Hello, this is BioBeat, brought to you by Biotechnology Board in Pittsburgh, Pennsylvania. I'm Kanak Iyer, a co-founder of the board, where we bring life-changing innovations to life. Our goal is to make Pittsburgh a hub for global partnerships in biotechnology. With my co-host Bill Flanagan, we host this every twice a month and bringing some of the leaders in the region in biotechnology. And today we have a special guest who runs the McGowan Institute for Regenerative Medicine, Dr. Sen. Bill, would you do the honors to introduce our guest?
I absolutely will, Kanak. Great to be here with you again to talk about some of the exciting things that are happening here in our region in terms of biotech and life sciences. And our guest today is on the cutting edge of all of this. You know, it is quite a journey from Calcutta, India to Pittsburgh, Pennsylvania, with stops at the University of Eastern Finland, Ohio State, and Indiana University along the way. Yet that's the path Dr. Chandan Sen has followed to our region. As Kanak mentioned, he's a renowned expert in regenerative medicine and a pioneer of novel wound care technologies. And about 2 years ago, he joined the University of Pittsburgh School of Medicine and UPMC and also took the helm of the McGowan Institute for Regenerative Medicine. And Dr. Sen, a belated welcome to Pittsburgh. Thank you for joining us today.
Thank you. Thank you. Pleasure to be here.
Yeah, maybe we can start with your journey, because it is rather remarkable to get your start on the other side of the world. What sparked your interest in regenerative medicine and in wound care in the first place?
So I learned about regenerative medicine and wound care much later. It started with interest in developing a scientific career, because of which I was in this European program, and the European programs are quite different. The initial interest was to be in a US program, but then once I was in Europe presenting at a conference and I saw the way the European programs are set up, I was very excited about it and ended up getting a fellowship and therefore joined a Scandinavian program, because of which I spent some time in Finland, spent some time in Stockholm, in Sweden, and in Denmark, in Copenhagen, and also a substantial amount of time in Japan, at Osaka University, during my PhD years. And at that time, it was mostly dedicated to understanding how science works. And eventually, once I was done with my PhD program and came to the University of California at Berkeley to do my postdoc, I was in the Department of Molecular and Cell Biology. One day, in the second year of my postdocship, unannounced, a very famous person entered my office, and I did not know, and this was Professor Thomas K. Hunt, who is also known as the father of wound healing in this country. And he just walked over into my office, did not call me. He was from UCSF, University of California, San Francisco, and leading one of the country's largest wound care programs, as well as what is known as the trauma center at the time, and said, Chandan, I've been reading your works, and it's wonderful science, but you're not putting it to good use. And I see a connection between what you are studying. At the time, I was looking at how oxygen and derivatives like oxygen-free radicals and peroxides participate in cell signaling, and he thought that science had a lot to do with how wound healing could be improved. At the time, I had no clue what wound healing was all about. So he informed me of how wound healing is, and he said, look, I'm writing a proposal, and I want you to be one of the PIs of this large, what is known as a trauma center grant for the National Institutes of Health. Long story short, I became a project PI, the proposal got funded, and I got into wound healing research. Regenerative medicine arrived much later.
Interesting. Well, what is it about wound healing that makes it, I guess, such a challenge, but also an area worth exploring?
So first and foremost, wound healing, the science and medicine of wound healing is terribly underappreciated, because people think of wound healing as a local problem. But the fact is that when we get wounded, we repair ourselves, and that's physiology, And when a wound appears in the body for some reason and does not go away, that is just symptomatic of the fact that there are a lot of underlying conditions that complicate your health. So a non-healing wound is only an indication of many other problems in the body, and it's not a local problem, it's a systemic problem. So when you don't recognize that as such, as is the case today, as I view even in the healthcare today, the wound is viewed as something of a peripheral problem to be taken care of by wound care specialists, but it really requires a much more integrated, care delivery to be addressing wound healing. So in this case, the wound then ends up infecting your bone. The bone infection then ends up being a threat to your life, and then to avoid that threat, you undergo a minor amputation, often followed by a major amputation. Once you get a major amputation above your knee, your chances of living the next 5 years is roughly 50%.
Really?
So that's it.
That's significant.
That's it.
Wow.
So most people don't realize that. And by the way, when somebody does die because of it, they actually would die out of a heart failure, and you would not even connect it to the wound. But it all started because the blood is now thrusting back to your heart, and the heart cannot take it because of a shorter limb, and it dilates. So that heart failure is connected to the ulcer that you had. So this connection is not typically made. So it is a systemic problem that needs to be addressed.
I always hear this in the context of diabetes especially, and that has huge economic
Impact,
implications
yes.
as well as health implications for the country. Is that a particularly acute area where this becomes a concern?
Absolutely. The diabetic foot is one of the largest problems we have. But having said that, pressure ulcers are very common on people lying on the bed, and now you have that pressure ulcer. And if you think about Christopher Reeves and how he died, we all know about the spinal cord injury, but the fact is he died because of an infected pressure ulcer.
Wow.
So in other words, those other better known diseases, so to speak, get the limelight. But once you have an infected chronic wound, it takes away your life. It takes away your extremities, and then your life in some order. So a more holistic approach to really solve the problem of wound healing is necessary.
Well, Kanak, this really gets us into the science. Absolutely, pick it up.
So tell us about your tissue nanotransfection technology that you pioneered.
Tissue nanotransfection. So a brief background before I get into that. So normally you see there are cell types in the body that can make other types of cells, and broadly people call them stem cells. And the good news of stem cells is that ideally a stem cell could make any of the 200 plus cell types that are needed in the human body. The bad news is only some stem cells listen to you, others don't, and then when you inject those cells into the body, some stem cells could end up becoming a cancer cell, and then the treatment has to be stopped. So there are safety concerns. Now the interesting part is that as time has elapsed, we have learned that not only the stem cells, but there are other adult, as we call them, adult somatic cells or adult cells of the body have some plasticity that and some limited stemness that can be leveraged to rescue the function that we intend to rescue. In other words, in all cases, stem cells are not necessarily required. So you could leverage the stemness of your non-stem cells.
You did the skin cells.
Exactly. In our case, we did the skin cells. So TNT has two significant components. One, in which it is a technology that leverages the stemness of skin cells in the intact skin of the body and achieves the generation of, say, vascular cells to make blood vessels, or neural cells to make components of the nervous system, or what have you. Several outcomes can be achieved, and for this you don't need stem cells, but more importantly, you don't need a laboratory. All of the reactions take place within your body. So one major attraction for us is, even if all of the stem cell world discoveries were to work in the way we intend, a very small fraction of the patients that require that type of care will get it, because it will be extremely expensive. The GMP grade manufacturing of the tissue, so on and so forth, taking that into live body, struggling with the body's immune system, now rejecting that piece that was made in the lab. So in our case, it's
even with your own stem cells, it can be rejected?
Yeah, absolutely. Many cases of such. But in our case, a a silicone chip touches your body 1/10 of a second, goes away, never touches you again. And now the skin changes its function and achieves the function that you need. In one case, in a say, a mangled limb, you need blood vessels. So now you are generating vasculogenic cells or blood vessel generating cells out of skin cells, and the blood vessels will go rescue your mangled limb in one case. In another case, you would be making neural cells or nerve cells, nerve-like cells in the skin, which in 3 weeks will achieve the electrophysiology of the nerves. And then you harvest them from the skin, put them in the injured brain, recover brain function.
So Parkinson's, for Parkinson's?
Yeah, we did not use for that, but in theory, this is the type of technology that could be used. In our case, we were more interested in traumatic or brain injury or stroke, or but to renew the neural supply of the central nervous system, this could be a potential. These are your own cells giving rise to your own
the dopamine producing cells, you know,
which then can be transplanted.
Yes, the non-scientist, though, I got to ask you, what's going on with this chip? You're touching a chip against the skin, and somehow it's modifying the way the skin, the cells in the skin operate?
Happy to expand. So you see, think of it if you're thinking at home, and if I a little bit step out of scientific explanation. So you can think of regenerative medicine as one of two ways, primary ways. One is where you take different types of cells and the cement and the different components and think like an engineer and reconstruct the tissue in the lab, and then you take it to the body. And when you take it to the body and the immune system complains, you try to put the immune system to sleep partly or wholly to make sure the tissue is accepted. So that I would call the tissue engineering approach. Now, for a second, think of making a baby using that approach. It would take you 1,000 scientists and you could still not make a baby.
It's an infinite problem in a lot of ways.
You cannot.
Yeah,
However, you don't need any scientist to make a human baby. Babies are made all the time. So that is the developmental pathway, where if you have the right genetic code, the entire body will be made. So that would be the whole baby. But you cannot make the baby because that would be ethically problematic. So you only make the part of the baby, in this case, or use developmental biology to make the body part you need. So that's what you're playing out. Instead of the uterus, you're playing it out in the skin.
I think about a salamander regrowing a limb. It's got something going on inside that makes that possible.
But in this case...
I asked him that question. Salamander can grow an arm, why can't we? I asked him.
So you see here, we have been given some reparative and regenerative powers. Those reparative and regenerative powers are best unfolded in the uterus. So if you went into the uterus and you caused a wound, the baby would be born without a scar. Perfect regeneration would take place, only in the mother's womb. So one line of pursuit is to actually recapitulate developmental biology in places other than the uterus, in this case, the skin. So that chip delivers genetic signals, which then makes or converts the function of the cells of the skin into some other intended function for rescue. And that's what exactly is achieved by TNT or tissue nanotransfection.
Actually, you made a difference even in journalism. You know, today what he did? He sent me a note saying, Dr. Chen. I said, he turned a Bengali into a Chinese. Exactly like that. You did nanotransfection.
I don't mind. I don't mind as long as the science is communicated. I don't mind.
So that's it, exactly.
But another key part in the layman point is that because of the simplicity, now whether it works and how well it works in the human is yet to be seen. But if it does work, because so far it is working in rodents, it's working in monkey, it's working in pigs, it's working in body parts of the human. So we take the abdomen of the human that comes off during what is known as abdominoplasty, and people undergo such surgery, and we put that in a bioreactor such that it lives for the next few weeks, and in there we test and it works, meaning now we are getting ready to go into the live human. And all these other steps are necessary to make sure that your risk is managed before you actually go into a live human. But if it does work, hypothetically, if it does work, you can democratize regenerative medicine in that it would cost you pennies to really roll it out. You don't need a lab. This can happen in the remotest part of Africa. We have support from the Department of Defense with the argument that this can be played out under austere conditions. So it is the chip, It is a small spark of electricity delivering that. And now, previously we used to do it, plugging it in the wall. Now we have a handheld click. You click it and the gene gets delivered.
Remote control.
Yeah, so you don't, it's just a piezoelectric power originator that then delivers, and that's all you need. So we'll see. It's the simplicity, and it is the opportunity of really scaling regenerative medicine solutions to the mass.
And so that's the potential. That's where that's kind of, you're sort of poised to figure this out. Can this really work? Because one of the challenges I could see is the scalability of any of these technologies.
Exactly.
So expensive, and everybody's different, and every problem. So with this Spark, the idea is you're different than me, we're different than her, but it would adapt to the particular individual.
The developmental biology signals are not so different. The type of barriers we are seeing is, if I am diabetic, then this cascade of biology that is supposed to happen in the skin has some barriers, and we recently recognized those barriers. But we also, using the same chip, can do gene editing and take down those barriers, and then we can enable it.
So it's like gene therapy. You're going
yeah, but it is a bit more sophisticated than single gene therapy, because gene therapy, you deliver the gene that you want expressed. Here we don't deliver that gene. We deliver an upstream signal that ends up making a tissue niche, which then keeps on generating the product of interest. So we do not deliver. The particular gene therapy is a more linear process where the product of interest, you deliver the corresponding gene and then essentially get the product to work and come to your rescue. That is not the intent here. This science is called reprogramming of the skin.
Right.
We reprogram the skin from being a skin into switching functionality towards therapy or rescue.
And you mentioned you're doing this in animal studies, and it's promising. You're seeing
Yeah,
very positive results.
Yeah, we published more than 20 papers, and it's in reputed journals. And the first time this was published, it was published in one of the top journals called Nature Nanotechnology, because there's a nanotechnology, and Nature Nanotechnology is one of the best known journals ever since we have. But there's more work to be done, in taking this to people. And now, it's a matter of a few weeks ago, Pitt has decided to commercialize this. So we are now going through a process within Pitt of commercialization. I'm glad that we have traveled, I'd like to say, almost 10 years. It's like 8 years or so of a distance. And now we are ready to go to people, which is, quite remarkable.
That is. In life sciences and biotech,
science.
it usually takes forever.
Oh, this is amazing. It's right now. And what are some of those moments, that aha moment, when you looked at the petri dish or something and said, wow, that's it? What are those?
So let me tell you. First of all, I'm sitting here telling you the story, and the audience may be misled to think that, I'm this guy that is making it happen. First and foremost, it takes a team of people that are interdisciplinary in nature, that think of it very differently. And, I'll tell you a small story, and maybe it gives you, and it's not the aha moment, but some type, something close to it. So when our team moved from Ohio State to Indiana, and in Indiana there is a noted vascular biologist, and we had just reported in the literature that we can make, blood vessel generating cells in the skin. Which can then make functional blood vessels flow blood and rescue. And so when I met Dr. Yoder, who is a very recognized vascular biologist, and he gave me a smile, and the paper was already out, and he said, there could be a mistake somewhere here. I don't think this is possible. So that's what he told me.
Wow.
Of course. That's
and he was the director of the Children's Institute there, a very noted a scientist in stem cell biology, vascular biology. And so I sat down with him and I said, Merv, what do you do now? He said, I retired and I'm working in the dean's office. And I said, are you interested to come back to science? And he said, yes. I said, why don't you join us as the director emeritus of our institute? Go to the lab and tell me where we are wrong. And unless you tell me, I'm not going to publish the next paper. I'm going to put things on hold. And you tell me where we are wrong. So he goes in there, and I also told him the next paper we publish, I'll only publish if you co-author it, if you believe in this. Because other critiques I cannot convince, but here you are, somebody in front of me. So from that point on, all the papers. Merv has been a co-author. He said that I never knew that this could be possible.
Yeah.
When we moved to Pittsburgh, he's now working here with us in Pittsburgh. And so he went through this process of a very critical vetting. It cost us a lot of time and money, but I thought it was really worth, and also for the postdocs and the grad students to have access to another noted scientist who would ask very difficult critical questions, and for them to be generating the data to show him and to show him the raw data. So then when he said, Chandan, this is really something impressive, and I would like to carry on with this. So when we were coming to Pittsburgh, he said, can I go with you as well?
Okay.
So that's
Yes.
a moment where you say we're doing something right.
Sure.
Yeah.
So now you said blood vessels. How about blood itself?
Yeah, so in this case, blood, as you know,
Yeah.
these hematopoietic cells are made in the bone marrow.
Mm-hmm.
In the case of a mangled limb, blood is not a problem. The vessels are gone.
Sure.
So in our case, we have made nerve cells, or as we call them, neural cells that have electrophysiology of nerve
Sure.
cells. We have made blood vessels, and we are about to report, we did not yet report that, but we are now writing up the manuscript, that using this one-touch chip on the skin, under the skin, you can develop what is known as a beta cell niche. And the beta cell niche will measure your blood sugar, and when your blood sugar is high, only when your blood sugar is high, will it start making insulin, all the related hormones, and take the sugar down. When the sugar is down, automatically it will stop.
That's fantastic.
And
yes.
that works for the next 8 weeks.
Yeah.
So this is a single touch, no insulin supply needed, no cold chain needed. So affordability wise, so we're working on that.
That's a
right
feedback
now.
loop.
Yeah, it's a feedback loop. So we developed this, what we call a beta cell niche under the skin. There is no inflammation, there is no irritation. So now we are trying to take that to people. So we'll see.
Fantastic.
That is
Absolutely
incredible. You mentioned doing here in Pittsburgh. I mean, you have been connected with some very prestigious programs already. What made you decide to bring the team here to our region and do this work here?
First and foremost, you may already know, but I'll still repeat this. In McGowan Institute for Regenerative Medicine has been here for a long time, delivering a lot of success to the market. I'd like to say like 32 years. And
I covered the story when it was set up.
You covered the story.
Ago, so I remember.
And I was only, a growing postdoc and reading from the outside the developments in McGowan. And the focus in McGowan has not been just good science, but good science taken to solve people's problems. And that is a very lofty goal, really, and it's a heavy lift. And so when the opportunity arose, fortunately or unfortunately, there's nothing much I can do on my own. I need my team. And Pittsburgh was ready, so 43 people arrived.
43 people
yeah.
came here with you?
Yeah.
Oh my gosh.
With 12 faculty or so, and they all,
Amazing.
and by the way, I did not recruit them. It's the opposite. I asked them to stay back in Indiana because many of them had their settled families and all. But interestingly, they resigned and they said, we want to go with you. And, and I spoke with Pittsburgh and they said, if that's the case, we'll accommodate all of them.
May I read to you what Dean Shaker said? He said, it's impossible to encapsulate the collective impact of Chandan's pioneering research and continuing breakthroughs in tissue repair and regeneration, said Dr. Shaker, Dean of Pittsburgh's School of Medicine. The work of Dr. Sen's team will accelerate Pitt's momentum in research areas that are key to the future of the region and drive the collaboration with other biomedical innovators, including Carnegie Mellon University. There you go.
Very kind of him, very kind and generous of him. But
so you're going to make our dreams come true, making Pittsburgh a hub for global partnerships in biotechnology.
I'd love to, and you already have a massive momentum going on here. So we'd like to draw strength from it and hopefully give back to it in a way, because we all are a pebble, and we need to really come together to form that critical mass. And one thing is very clear to me: the future of biotech is not the same as the past of biotech. It's a very different recipe. In fact, I believe if you are very good at today's biotech, that's a hindrance to actually be the seed of tomorrow's biotech. Tomorrow's biotech is very different than yesterday's biotech.
In what respect? What's
In many
changed so
respects.
much?
I'll give you a couple of examples. The past of biotech has been, or the current success of biotech, you have products that can be scaled across the board. Going forward, it's going to be much more tweaking with respect to individual needs.
Precision medicine?
Yeah, precision medicine, the manufacturing component of that, as you know, is very different. The future of biotech will have a major role of machine learning and artificial intelligence playing into it.
We are right there at the top with Carnegie Mellon. Yeah.
Absolutely, and you have tremendous strength around Pitt, as she mentioned, and other parts include you really would have to be more sensitive to scaling the solution, in a way that fits the need of particular cohorts. And again, coming to precision medicine. So it's not the same. It's very different, and it's very encouraging to see that BioForge has been seeded exactly with that in mind. So we are in the right place at the right time. So I believe that
sky's the limit.
Western Pennsylvania is set to emerge as
so we're going to talk about his role in the Appalachia becoming a big force in biotech workforce development.
In workforce development, our next podcast, right? Well, we can dig a little deeper in that space for sure.
Yeah. So now, if I may, you're also connected to Harvard's Joslin Center. So how are you bringing all this interdisciplinary and changing our landscape here in Pittsburgh?
Yeah, so the background to that is that the U.S. Congress has asked the NIH leadership to have a program that will bring down the amputation of people affected by diabetes. So as a result of which, the National Institutes of Health has instituted a diabetic foot consortium. And the diabetic foot consortium at this time in the country has 4 major pillars. We are one major pillar. And each major pillar gets to appoint or select 2 satellite sites. So we got to select, Joslin at Beth Israel as one of our satellites. So now Pittsburgh is one of the primary pillar, and Joslin is a satellite. And then we are looking forward to a second satellite. And I'm very interested to bring in really UPenn. I was last week speaking at UPenn, and we'll see if that works out. There are certain criteria. But that's our relationship. Yeah.
That should make Governor Shapiro happy, right?
Well, absolutely. And I wonder, you look into the future, 5 years, talk about the end of the decade, maybe a decade beyond that. What do you see as the potential, if this remains funded, if you're able to pursue this as aggressively as you are right now? What's the potential? What could change as a result?
First and foremost, before I answer that question, I'd like to acknowledge the effective partnership between UPMC and Pitt is central to making or taking science to impact on people. And McGowan is, I think, privileged to have now research presence in 20 hospitals, be it Altoona, Hammett, Cumberland, all these places. We have research sites, and they all belong to, we call it the Pitt-McGowan Wound Research Consortium. And so this arrangement between UPMC and Pitt that gives Pitt scientists access to shaping the healthcare delivery process is critical.
It's not just you down in your lab on the Mon River
so it's
in Pittsburgh.
into mainstream healthcare? All that?
Absolutely, absolutely. And I'll give you, just this week, we have a technology developed in Switzerland where they wanted, for wound care, diabetic foot care, wanted us tested here in Pittsburgh. We are now starting the site in Altoona. So we have a Pitt staff team, including centrifuge, freezers in Altoona. And after that, we have another major company from UK called Convatec, a multi-billion-dollar company. And they would like to test some of their products, and that's happening in Hammett. McGowan is the hub. But we have now footprint across the state. And so that's enormous. And I think that no matter where science goes, of course science is very exciting for us. At the same time, we have to show that we are impacting people, and the amputation rate in Pennsylvania is dropping. Amputation in Pennsylvania is a massive cost to the state.
Older population here, lots of factors.
Not only money as well as lost productivity equating with money, massive cost. If we can start giving relief. So this science and discovery is not just a matter of
Some ivory tower thing, but it is
fancy.
very,
It's really serving people. We use taxpayer dollars, and our commitment is to bring back value to the people we serve.
Definitely.
Wow, it's an incredible story. I think we're about
It's
out
amazing.
of time
It's
for
amazing.
today's podcast.
And so, what keeps you inspired? I mean, keep on going. Like an Energizer bunny. I mean, anybody who comes in contact with you can see that. They'll say, "We want to do what he's doing." A young student, in a school or college.
Personally, I'm a person of a very modest background, and I feel blessed that I have the privilege to be participating in efforts like this. And as long as that privilege is there, so two things, as long as that privilege is there, and as long as I see the talent pipeline of youngsters trying to grow up, because we're going to be there for a particular period of time, and the only way our work is going to bear fruit is we ensure, while we are sitting in our positions, the right plan for bringing in the new leaders and developing the next generation of talent. So this is an enormous opportunity. This is priceless. This is something that is coming our way, and therefore there is it's automatic that you wake up every day and you have a big shoe to fill and lots of deliverables to provide. It's very exciting.
Well, you have done a wonderful job of teeing up our next podcast when we'll talk about those scientists and caregivers of the future. Dr.
It's such a privilege to know you and know your science.
Thank you for having
And
me.
it's our responsibility to get it across to the rest of the world.
It's my privilege to be a part of this community.
Excellent. Thank you so much.
Thank you. Thank you. Thank you.